Hello, my name is Kristian Lehre. I'll present joint work with Duc-Cuong and Anton Eremeev. So in this paper, we're making two contributions. First, we are connecting fitness landscape analysis with runtime analysis. So in fitness landscape analysis, we're interested in trying to determine something about the hardness of a problem from the structure of the fitness landscape. So we're going to introduce two notions called alpha dense fitness values and epsilon sparse local optima. And this leads to a problem class called SparseLocalOpt. The second contribution we make is that we make a strong separation between elitist evolutionary algorithms and non-elitist evolutionary algorithms. We will prove that for very large classes of SparseLocalOpt, any mu plus lambda elitist black box algorithm will have exponential running time. And for non-elitist evolutionary algorithms, we will demonstrate some sufficient conditions for these algorithms to be efficient on SparseLocalOpt. So fitness landscapes of complex combinatorial optimization problems have typically several local optima surrounded by fitness values. And we believe that one feature of fitness landscapes that contribute to the difficulty is the sparseness of the local optima relative to the fitness values, to the density of the surrounding fitness values. So these are kind of the intuition behind the definition that we're going to propose here now. So we said that the Hamming shell at radius r around a bit string x is all bit strings at distance r from x. So it's easy to see that the size of the Hamming shell is n choose r. So we say that our set A is alpha dense with respect to a set A prime if the following holds. So for any element x in A, the fraction of the Hamming neighbors of x that belongs to A prime needs to be at least alpha. Okay, so let's look at the definition of an epsilon sparse set B. So here in this illustration, these blue regions correspond to the set B. So now we say that B is epsilon sparse if for all x in B and for any radius r, so let's say this is x. If you're looking at the fraction of elements in the Hamming sphere at radius r around x that falls within B, it should be at most epsilon. And if we pick any search point x outside B, and we're looking at the fraction of elements in the Hamming sphere with radius r around x that falls within B, it should be at most 1 over n fraction. Okay, so let's now define the problem class. So we say that the pseudo-Boolean problem belongs to SparseLocalOpt alpha epsilon if we can construct a partition of the search space into a polynomial number of levels satisfying these four conditions. So for the full details, I recommend to read the paper, but I will here focus on the most important condition. So now, these levels should broadly follow the fitness values. However, we say it might be impossible to construct such a perfect level partition. So we say that a pair of levels AI and AJ are F deceptive if AI comes before AJ, and there exists a search point in AI which has fitness at least as high as some search point in AJ. Okay. Now call this the first element of the pair. We call this the fitness peak, and the second pair we call it the fitness valley. Okay. So what we require is that if we collect all such pairs and we take the union of the fitness peaks, we require that these are epsilon sparse. And if you take any fitness valley, we require that the fitness valley is alpha dense with respect to AJ and levels above AJ. This means if I'm in a fitness valley, at least an alpha fraction of my neighbors are within level j or higher. So if you look at the roles of alpha and epsilon, these are in some sense constraints on what problems can belong to the class. So if you choose epsilon very small, it means that any local optimum has to be very sparse. And if you choose alpha very large, it means that the fitness values needs to be very dense. In the other extreme case, where alpha is 0 and epsilon is 1, we essentially have no restrictions on the local optima and on the fitness values. So, by looking at SparseLocalOpt for different values of alpha and epsilon, we get a kind of a problem hierarchy. So I'm trying to draw this now in 2 dimensions. So on the x-axis I draw 1 minus alpha, and on the y-axis I have epsilon. So the closer I get to 0 on the x-axis, the stronger requirement I have on the density of the fitness values. And the lower I get on epsilon, the sparser the local optimum has to be. Okay, so SparseLocalOpt alpha epsilon is essentially all the problems that fit within this these constraints for the value of alpha and epsilon. So clearly, if I choose now a larger alpha, a smaller alpha, and larger epsilon, so let's say alpha prime and epsilon prime, I get a larger problem class. So we can now classify problems and problem classes within this square. So 1 max, we have really no local optima, so we can put it down here into the simplest corner. Needle in the haystack, it is kind of deceptive in some sense, so the only way we can put it is here at the upper right corner. And other problems, if you look at some instances, for example knapsack, you can find that there are some intermediary here. Later we're going to look at a particular problem called BB funnel that has 2 parameters alpha and epsilon that coincide with this SparseLocalOpt alpha epsilon here. Okay, so now we have defined a hierarchy of problem classes. And for each problem class now, so for each value of alpha and epsilon and a particular algorithm I'm interested in finding out, will this algorithm have polynomial worst case runtime, expected runtime on this problem class. So we're going to look at the elitist algorithms. So we'll now define the class of mu plus lambda elitist black box algorithms. So the algorithm knows that it needs to optimize some fitness function, and it knows that this fitness function is chosen from some class f, but it doesn't know exactly which function it's chosen. So the algorithm needs to obtain information about the fitness function. It asks an oracle about the fitness values of different search points. Now we make the additional restriction that the algorithm only remembers the mu fittest observed search points and their fitness values. So this is the only information that the algorithm uses in each round. So for each round, you use that information to sample lambda new search points. And for these new search points, the oracle will tell the function value. So the running time of such an algorithm will be the number of queries, the number of search points it asks for the function value, before the optimum is evaluated for the first time. And we say that the mu plus lambda elitist black box complexity of class f is the worst case expected running time of the fastest algorithm within this class. Okay, so for a given class f, if the elitist black box complexity is exponential, it means that any algorithm within that algorithm class will need at least exponential time to... Okay, what can we prove about this class? So for any constant delta, and assuming that mu and lambda are polynomials, the elitist mu plus lambda black box complexity of SparseLocalOpt 1 minus delta delta is exponential. So it means if we go to the simplest or the most constrained problems, right? So we have arbitrarily high density of the fitness valley and arbitrarily low sparsity of the local optima. We get some very, very small problem class, and still we can prove that any elitist algorithm within this algorithm class will have a worst case running time which is exponential on at least one problem in this class. To prove exponential mu plus lambda elitist black box complexity, we apply Yau's min-max theorem. So what we need to do is to choose any probability distribution on the problem class, and then we need to prove that the best deterministic black box algorithm has exponential average case running time on this problem, and we sample the problem from this distribution. So the problem we consider is called BB funnel. So it has one local optimum at the end of a long random path, a large fitness value here, and then a global optimum here. So any deterministic mu plus lambda elitist black box algorithm with the high probability start in the red region, and then it will need quite a long time to overcome this long path. And before it reaches the local optimum, the mu fitness individuals will already be on the path. And from that point on, the only thing the algorithm can do is to jump across the fitness valley, because it will never accept any search points within this alpha dense fitness valley. So we now consider a class of non-elitist evolutionary algorithms. So this algorithm uses a ranking-based selection mechanism. So we describe this in a very general form. So we imagine that the algorithm has a function beta, which is a cumulative density function. Now, so to select an individual, the algorithm sorts the population according to fitness, with the best fitness first, and then it now samples the index I such that the probability that I is less than gamma lambda equals beta gamma. Okay? Once it selects an individual, it applies mutation, so bitwise mutation. So each bit is flipped with probability chi or n. So by repeating this lambda times, we produce a completely new population, and we just continue with the next generation. So as a second result of this paper, we will see conditions, sufficient conditions, where non-elitist algorithms are efficient on this SparseLocalOpt problem class for a wide range of alpha and epsilon. So the first condition says that there should exist some psi naught such that for any gamma above psi naught, beta gamma is less than this function u of gamma. Okay, that's something that depends on epsilon and the mutation rate. The second condition says that for all gamma between 0 and gamma naught, beta gamma should be at least this function L gamma, and this is a function of the mutation rate. Okay, so if you observe here now, L gamma is larger than U gamma. So this means that the only way for this beta function to satisfy both conditions is that it's non-linear, right? Any linear choice of beta is going to fail. Final condition says that beta of psi plus gamma minus beta of psi should be at least this quantity. Okay, if these three conditions are satisfied, then the algorithm will have polynomial time. We assume now logarithmic population size bounded by some polynomial. And we can find positive examples of this for particular settings. So for example, if you use two-limit selection with tournament size 3 and use mutation rate parameter chi 1.09812, so this is quite close to the error threshold, a little bit below the error threshold, which is log of 3. Then if you choose alpha to be at least 1 over 4 and epsilon to be less than 7 divided by 10 to the power of 5, then the conditions are satisfied. Another selection mechanism, if you use linear ranking selection with parameter eta equals 2, if you choose the mutation rate a little bit below the error threshold, which is in this case is log of 2, and alpha is at least 4 over 9 and epsilon is 1 over 100, then linear ranking selection will also satisfy this. But as I said, if you try to satisfy these conditions using mu comma lambda selection, which has a linear beta function, you will not be able to succeed. Assuming now the algorithm satisfies these conditions, we can analyze the relationship between two stochastic processes. One representing the number of individuals which are on the local optima, and the second process is how many individuals we have in a fitness value. So what we can prove is that if the selection mechanism satisfy the conditions, the proportion of individuals on the local optima will gradually decrease down to some, at most a fraction psi naught. And then once we have no more than psi naught individuals on the local optima, and we have some but not too many individuals in the fitness valleys, the probability of sampling an individual in the fitness valley becomes xt over lambda times 1 plus delta, where xt is the number of individuals we have in the fitness valley. So essentially, the proportion of individuals in the fitness valley will increase. And this is essentially condition G2 in the classical level-based theorem. So to conclude, we've made two major contributions with this paper. First of all, we have connected runtime analysis to fitness landscape analysis. So previously, these has been two separate sub-communities in evolutionary computation theory. The second contribution we made is a very strong and general separation between elitist and non-elitist EAs. So for the very broad class of elitist mu plus lambda black box algorithms, we proved that they will fail even for mildly deceptive problems. In contrast, we provided sufficient conditions for non-elitist EAs to optimize highly rugged fitness landscapes. And what we observe is the essential characteristics of the algorithm is that it should have a nonlinear beta function. So we see that this is not the case if you use mu comma lambda selection. However, it's the case if you use tournament or linear ranking selection. The second characteristic that the algorithm should have is that the mutation rate should be close to the error threshold. So, in future work, we would like to classify evolutionary algorithms in terms of SparseLocalOpt. And it's also interesting to classify existing problems according to sparse density.